We'll finish up today with the Michael reaction. Michael addition. Let's finish that up. Michael. Arthur Michael was his name. American-born chemist, trained in Germany under a chemist by the name of Hoffman. Ever heard of Hoffman? Is it something related to elimination, I believe? Michael also trained under Robert Bunsen. Bunsen did something with some type of burner in the lab. You now call it the Bunsen burner. Okay, Michael. How would you make these compounds? Well, this one was made above. Somewhere you can look there. From cyclohexanone. How about the one in the middle? How can we make the compound in the middle from cyclohexanone? What do you want to do? Just react this with what?
Br2 and HBr.
Just with dimethylamine?
No.
No, that would give we need a leaving group here.
Or
Want to convert this to something like this. Get a leaving group there. And then we can come in with an amine and do an SN2, kick that off. How are you going to put a bromine there?
Can't.
You ain't going to do it. That's right. But we can react this with maybe bromine and maybe acetic acid. What's that going to do?
It's going to put a bromine next to the carbon.
We can put a bromine next to carbonyl, alpha halogenation. Leaving group's in the wrong place. What can we do next?
Potassium terbutoxide.
Let's do potassium terbutoxide. Let's do an E2 elimination, and let's get to the alpha beta unsaturated ketone. Yeah? Now we can add a nucleophile to the beta position. We don't have a leaving group. Well, the pi bond's sort of acting as a leaving group. It's a nucleophilic addition. Now we can come in here with dimethylamine. Is the dimethylamine going to react with carbonyl and make enamine, or is it going to add here? One equivalent. Amines prefer what?
One.
Amines prefer to react with these alpha beta unsaturated carbonyls at the beta carbon. And then electrons here, electrons there, yeah. And then proton transfer, positive nitrogen, H here, anion proton transfer. Okay, that's your Michael addition. There we go. The Michael addition gets you nucleophiles at the beta carbon. Okay? But you see the chemistry leading up to that? Okay? It'd be very hard to put a halogen here. Very hard to get a leaving group there. But we can do this and still don't have anything here. Still, nothing's going to react here. But now we have this electrophilic site. Okay? How would you make the one over here?
Same thing as before.
Same thing, except you're going to react this with what?
Methyl magnesium bromide.
Like methyl magnesium iodide or bromide. followed by what?
Workup.
Yeah, you need H plus workup, yeah? Because Grignards prefer to add how?
1, 2.
1, 2, which is what that is. That's a 1, 2, if you can envision that. Yeah? By the way, when you do a Grignard, you preferentially get 1, 2. You might get a little 1, 4. Of course, any product we always say the major product. Does that mean you can't get some minor product? In many cases, you can get a minor product. 1, 2. It's actually an interesting experiment that was done. If you make Grignard and then react it here, you get like, I'm making these numbers up. This is percent 1, 2, this is percent 1, 4. If you use regular magnesium to make your Grignard, you get something like that. If you use super pure magnesium, you get something more like this. In both cases, we see the 1, 2 is favored. But why the difference between super pure and regular magnesium?
What's in magnesium normally then?
What?
What's in magnesium normally then? That makes it.
What's in magnesium?
That, or what would be regular magnesium that would cause it the 5%?
Okay, good. Okay. Well, it turns out there's trace metals in other metals. And there's a little bit of copper in regular magnesium. Okay? And it's been shown that if you use super purified magnesium, that you can decrease the 1, 4, to basically nil. And this apparently kind of suggests that trace amounts of copper in the magnesium were sort of promoting the 1, 4. Sort of an interesting.
Didn't you show that more solidly by just adding copper to your magnesium and see if there's an increase?
Well, that's known.
Okay.
You can, if you add certain copper to a Grignard, you're basically going to form the organic cuprate. I mean, that's how cuprates are made. You take an alkyl lithium and you react it with like copper bromide. But a Grignard will react just like an alkyl lithium. Okay, so thinking backwards using synthesis, a little bit of review. How do you make alpha, beta, and saturated carbonyls? We showed that earlier, reviewed there. Okay. History of superglue. Hopefully I have the other handout. I'll look at it this morning. The white handout, various things. Let's look at the toxicity of Tylenol. Do you know Tylenol is toxic?
No.
Yes, many drugs are toxic if you take too much. I believe toxic for Tylenol, I believe, is still 100 milligram per kilogram. It used to be the toxicity threshold. Does that mean 99 milligram per kilogram is not toxic? Well, I would not probably go to 99. Typically you don't give more than about 50 milligrams per kilogram. All right. So 100 person may weigh, well, big person, 100 kilogram. 100 milligram per kilogram, that'd be 100 times 100. What is that? 100 times 10 is 1,000, right?
Yes.
10,000? 10,000 milligrams, turn that into gram,
10 grams. So 10 grams.
10 grams. Okay? So for 100 kilogram person, 10 grams of Tylenol would be 100 milligram per kilogram. 10 grams of Tylenol, what is that? One extra strength Tylenol is half a gram, 500 milligrams. 20 Tylenol. Right? But that's basically a lot of drug, pharmacy, yeah? 20 Tylenol is going to be toxic. Does that mean 19 Tylenol is not? Or even 10? I don't know where that number comes from, but typically dosage, sometimes you hear on medical shows, let's administer 10 milligrams per kg of, need to know the weight of the patient. Okay, Tylenol in the body is oxidized. Tylenol is oxidized to this. Is that an oxidation? What's going on here? How do you know that? How do we know that's an oxidation?
More bonds to electron.
Because it says oxidation?
Oh, no, like the aromatic
We're losing hydrogen.
It is becoming carbonyl. Typically, that's an oxidation. Yeah, we're losing hydrogen. These two H's are gone now. Loss of hydrogen. That's the way to tell. Yeah. We're also destroying the aromaticity. This is known. These types of things, diols. We didn't look at this. I almost feel like we should because it's sort of common, but there's enough to look at anyway. But look at this, alpha, beta, and saturated carbonyl here, yeah? And nucleophiles love to add to these things. And then proteins have a lot of amino groups, and it can add to that, do a Michael addition, and now it can be covalently bonded here. Now this can eliminate, we'll see that in the next section. This can eliminate back off. But in this particular case, this thing's going to tautomerize. If this tautomerizes, we've got an H here and an H here. Both of these can relocate. If we relocate the top one, put double bond here and relocate it to the end, and the bottom one, let's relocate it to the oxygen and put the double bond here. That ring looks a little ugly, but the ring is now what?
Aromatic.
It's now aromatic. It becomes aromatic just through tautomerization, and you know what? It's going to tautomerize to that. But once it becomes aromatic, you're not going to eliminate that group back off. Much more difficult. And now your protein, or your DNA, is now stuck. It's covalently modified. It's going to cause problems if you got too much of this going on. Lots of proteins in your liver that can do this. And Tylenol can be toxic to the liver. If you take too much,
Is that all in one sitting or over the course of a 24-hour period? Those like
I don't know the
toxic
exact
amounts.
details. I'm sure you can find that. What protects your body from this, though? What does your body have that can protect it?
Glutathione.
Glutathione, yes. I showed you that in organic 1. Glutathione has an SH group. Okay? And instead of that, you have glutathione. And it's a sacrificial nucleophile. And it reacts here, and it protects your proteins. And it reacts with that toxic metabolite. That's a role of glutathione. Has a very nucleophilic SH group. And the problem is glutathione is limited. You don't have an abundant supply of it. And once it runs out, then there's nothing left to react, and then your proteins start reacting. So apparently glutathione can handle small amounts of metabolite and flush it out, get rid of it. If you get too much, and then other nucleophiles are going to start reacting. Question?
Is it the reason why the product is really favored with tautomerization is because it forms a phenol? And we learned that that's like a really highly favored, you know.
Well, you got aromatic ring,
I mean,
so the tautomerization is going to be very favored. I mean, this is tautomers are in equilibrium. Which tautomer is going to be favored? The one on the right is a double tautomer. I'm doing two tautomerizations, but this is going to be favored structure. And at this point, you're not going to eliminate this group off. It would have to be a benzyme to eliminate it off, and it's much more difficult to eliminate off. Yeah.
So like, I'm wearing like primary care, like the lead acronym, right? And so like N stands for like Narcan, for like anti-narcotic and stuff. So does that have anything to do with like the glutathione, like any like? Does it do like a similar mechanism to prevent like your body from?
Narcan?
Yeah.
That's for treatment of what? I'm thinking something else.
Like overdose of like something like fentanyl or like smoking or like.
No, I think that's a different mechanism. That's more of a physiological mechanism. I'm thinking of, well, overdose of Tylenol, they'll give you something called mucinist. That's what I'm thinking of. Isn't it mucinist? Anybody know? Maybe I'm wrong. But mucinist is basically another compound that has an SH group. Glutathione is natural in your body. Mucinist is just a synthetic analog of glutathione. You know, they give you that, and it goes in your body. It's like they're giving you more glutathione, but it's not exactly glutathione. It's something similar to help. But you can look it up. Overdose on Tylenol, that's what they give you, and it does it. They're giving you a nucleophile. We need to move ahead. Question?
I just wanted to know what part of our body makes glutathione? How do we make it?
I'm not sure. It's a tripeptide. It comes from 3 amino acids.
Oh,
One of them has an SH group. Which amino acid has an SH group? Cysteine, right? I know, yeah? Cysteine? Am I right? Yeah? Cysteine has an SH? Okay. Which one has an S-methyl? Methionine. Is that right? Yeah?
yes.
Okay. Those are the two that have sulfurs, cysteine and methionine. But the S-methyl group is not going to be nearly as nucleophilic. Okay, so, why didn't you tell me that was below? Why do I have to redo that? Chemistry of superglue. Reactions with these alpha-beta unsaturated carbonyl compounds are not easy. Because if you don't do it right, you're going to get polymer. Okay? Superglue. Superglue is methyl alpha-cyanoacrylate. Okay, look on the back of superglue next time you're in the checkout line at Walmart. It's usually hanging right there. Look on the back. It'll say acrylate. Okay? It can polymerize. How? Some type of nucleophile. This is an anion, right? Some type of nucleophile adds beta. There's a Michael addition. We've done this before. At this point, we just picked up proton, either from proton transfer or adding in workup. Yeah? What else could that anion do? It could react again. And this is where you have to be careful. If you're trying to do this and you just want to pick up proton, sometimes it won't listen to you. It'll just polymerize on you. And you have just this polymer you made when really you wanted a monomer from just a single addition. That's where it can be a little bit the way you do it, you know. But it can come in here, and this anion can do another microaddition. And what can this anion do? another Michael addition. And somebody stopped me. And eventually you're going to have a huge molecule, and this is polymerization. Okay? And with this particular molecule, when it polymerizes, it's going to form this solid, which also has sort of binding properties, and it will be a glue, super glue. Now this is called an anionic polymerization because it's initiated by an anion. Okay. In organic 1, we saw cationic polymerizations initiated by like H+. Okay, alkene there. You can also have radical polymerizations. All right. Polymers, there are other polymers. Instead of the cyano group, if that was just a methyl, that polymer is called, anybody know the name of that one?
Is it chewing gum?
Do what?
Is it chewing gum?
Chewing gum?
Yes. That's just a gamble.
No, it's not. I don't know what chewing gum is. It is. It's called plexiglass. Anybody heard of plexiglass?
Yeah.
Okay. Same molecule, except it's a methyl instead of a cyano group, right? Okay. Do polymerization here. By the way, can you show how the polymer? You show the polymer form with the conventional way like that. This polymer is plexiglass, also called acrylic. Heard of acrylic? Yeah. Because the common name for these alpha beta unsaturated esters is acrylate. Common name for those. And it's methacrylate. It's kind of a common name. It's got the methyl on it. And then this methyl refers to the ester group. Named as an ester. These are, if you look it up, PMMA on Wikipedia, that's where I got these pictures from. This is a car that's just total plastic. But acrylate tends to be a very thick, heavy plastic, or it can be made. Or some plastics, they're going to have to be real thin because they just can't, their properties don't allow them to be made thick. But acrylates can be made thick and very strong. I mean, I don't know if this is acrylate, but you see how thicker this is compared to something like this. Okay, something like polypropylene or polyethylene, they're going to tend to be thinner things. Also, transparency. Some polymers they just can't be made clear and transparent. Okay, but if you don't need it, then that's okay, and you can use certain type of polymer. One thing about acrylates are they tend to be stronger. You can make them thicker, and they tend to also be able to be made clear and transparent. Okay, polymer chemistry is a huge field, and of course in polymer chemistry there'd be enough to do a whole course in it. Okay. Now plexiglass is also known to be quite strong. Okay, stronger than regular glass. Okay, you might think, of course, I can break glass. Well, yeah. Plexiglass is much harder to break, and when it shatters, it's also safer. But it's known to be strong. So it's a very important polymer. There's certainly other types of polymers. There's polycarbonates, polyamides such as nylon. There's different types of polymerization that can take place. But this is coming from Michael chemistry. A Michael addition is the initiation of the polymerization. But then the resulting anion just keeps self-reacting. All right? We get that. Does that look like the polymer that would be formed? Again, nucleophile, that would be adding to the beta carbon. This is your ester group. Can I just say ester group with methyl? resulting anion. And this is going to end up being bonded to another beta carbon with an ester and a methyl. We made this bond. Anion, it's enolate, okay? But then instead of it picking up proton, it can add to beta carbon, ester, methyl, anion, but it's instead add here beta carbon, here, ester, methyl. What do we have here? After nucleophile, we have CH2, carbon with a methyl and ester, CH2, carbon with a methyl and ester. Okay, you see how it's repeating? CH2, carbon with a methyl and ester. Is that what's in the brackets? CH2, carbon, methyl, ester, and then it's just showing it repeating over and over and over. All right. Now, one below is actually in some of contact lenses, fiber contacts. Okay, it's a piece of plastic, yeah. Okay. Very similar to plexiglass, but the ester, instead of a regular methyl ester, it's got an additional carbon and then an OH. And so this ester group here, and this polymer has property of being more wettable and staying more wet. Okay. That's important with something in your eye. You want it to be more wettable, not just plastic bone dry. Why is it more wettable? Because it has this OH group, which is very hydrophilic. Can a plastic be wettable? It can be. I mean, can a cloth be wettable? What's the difference between like a rain jacket, which is made out of polyester, versus a cotton shirt, which is made out of polycotton? Cotton is a polymer. Which one's more wettable? If I told you that a cotton shirt absorbed water, would you think I'm crazy?
No.
You take a cotton shirt and put it in your sink with some water, it will absorb a lot of water. You take that shirt out, it's going to then weigh like 10 times more than when you put it in. It's absorbing water, right? Well, the same thing with polymers. Now it's not going to absorb that much water, but that's chemistry. They made the polymer with this OH group so it would be more hydrophilic, and apparently it's modern chemistry that's making better contact lenses. Probably so they're more wettable and less irritating and stuff like that. Question?
Yes. The chemistry department a couple of semesters ago was giving away a plastic cup where you pour something cold in it and the cup changed blue. Is that a polymer that just changes color when you make it cold?
I kind of doubt that the thing that's changing color is the actual polymer. It's probably impregnated or doped or something with some I don't know what that was.
All the polymers we've looked at in this class have always polymerized linearly. Are there any polymers that polymerize in a radial?
I don't know, but I would think so. There's branch type polymers. I don't know enough to give an example. Class on polymers would be interesting and a lot of information, a lot of practical information. The thing about polymers is, polymers you have to get into studying the macroscopic properties. Okay, I mean when we do, this is properties that we can see and use. Okay, and IMF is more of a chemical property with theory. This is like, okay, flexibility, transparency. These are more macroscopic properties. And making polymers, a lot of times they're not even worried about the molecular level. And sometimes they don't even know it. They make something and then say, hey, can I mold it into and make okay, it becomes a macroscopic science. Of course, there's at the molecular level, somebody had to know molecules and design this and say, hey, If we put an OH group in our polymer, would it become more hydrophilic? And indeed, it apparently did. And on the other hand, you could have did this and said, my polymer is no different. Well, then it was your experiment didn't work out, or your but you can look these things up on hard lens, soft lens, polymers, hydrogel by absorbing water. Okay. Super glue. Is that the last thing there? What have we not covered here? Wittig reaction. Have a Wittig synthesis of compound A, anybody? We also have in the Michael handout, a little bit there. Let's finish this up over here. We actually got some more over here. Michael addition. Can you envision a mechanism for this reaction here? It's like a substitution, right? Chlorine being substituted by the methoxide. What's the mechanism? SN2?
No.
No, not only, it's not a tetrahedral carbon. These electrons do a Michael addition. Michael addition, just because there's a chlorine there doesn't mean you can't do a Michael addition. What can happen next? Do what?
Electrons fall back in and kick off the chlorine.
Yes, exactly. This could pick up a proton. If there's, maybe you use methanol, it could serve as a proton source. That would be just a simple Michael addition, pick up proton. If you don't do this right, it might polymerize. This could react with another and do the polymerization. But this has something that's probably going to happen pretty readily here, is because it's internal. These electrons can come right back down and kick off the chlorine. And there you go. That would be an addition, a Michael addition, followed by an elimination. And that looks analogous to reacting. See, this here, this double bond carbon is analogous to this. Same thing here, nucleophile add, electrons up, and then back down, kick off chlorine. Electrons up, back down. See, this is a stabilized enolate. And we know that the electrons here are really largely on the oxygen, right? The resonance structure with charge on oxygen is really the major resonance structure. That's why it's called a 1,4 addition, right? If we add here, the electrons are largely on the oxygen, that's 4. Michael addition, also known as a 1,4 addition. All right? So an additional elimination, not an SN2, we can also compare this to, by the way, this is not going to happen. You're not going to do that there because there's no carbonyl. We only add nucleophiles to alkenes in this case where the resulting anion is stabilized. Just like down here, go to aromatic ring, we can do an NAS here, addition, elimination. If you ignore the fact that it's aromatic, that looks just like above. and that will work, but this will not. But NAS requires what? Strong electron withdrawing group ortho pair. Why was this able to happen? What was sort of the rule, or what do we say this is able to happen here? Because the resulting anion is put where? Onto a heteroatom. Well, it's the same thing with the reaction we did above. Because the major resonance structure, the charge is on the heteroatom. All right? Enolates, how do they act? Look at this reaction here. We got base here. We make anion here, yeah. Most acidic site. This can do a Michael addition. This is just a nucleophile doing a Michael addition. And the product is going to be well, if we do it just mechanistically, stepwise, doesn't that give that? Is that right? Well, this, if we just pick up proton, and this is why I kind of just wanted to do it there, I have to redraw the entire molecule. We can just pick up proton, and we then have boom, boom, boom. Maybe ethanol. Ethanol can supply proton. I suspect somebody's like, is that strong enough to supply a proton? Well, the alcohol is 16. What's the acid over here? That guy is 20. Which side's favored, 16 or 20? 20. So you see that side is favored. You got ethanol around.
But isn't there another acidic H right in the center between?
Very good. Very good. This may not sit like this. This may first do a proton transfer from here. Very good, and we're going to have to reevaluate that because now if we consider that age, this one is about 12, and 12 versus 16, it would not be favored. So very good point. This may very well need H plus workup. I agree. Thank you. Very good. Because instead of taking that age, which is 16, that one's about 12. Would this rather take us age 16 or age 12? Age 12. And this would be in step 1. And ethanol is not going to protonate that because that's ethanol is 16, that's 12. Very good, very good. So, you may have to add some external acid there. That's a Michael addition of an enolate is possible. But something else can happen here. We can keep going. Yes, this is a favorite anion. But we can also get some anion here. Equilibrium. All these anions are existing in equilibrium. Yes, the one we had over there is going to be favored, the most favored. That doesn't mean we can't get a little bit of this. And what can this do?
Back to carbonyl.
This can attack carbonyl. What size ring are we making? 6. 1, 2, 3, 4, 5, 6. Yeah? What does this give? There's the starred carbonyl. That's that. This attacked over here. Attacked this carbonyl that became O minus. This carbon has a methyl. Next door to this carbonyl, this carbon had a this. This ultimately, this can pick up proton. What's going to happen here? This can dehydrate. We're about out of time. I'm going to show you the product here. You know the mechanism, although based on your quiz, you may not know the mechanism. Double bond here, methyl. Is that right? There you go. That's a potential product that can be obtained from this reaction. A micro addition, which is top, followed by an intramolecular aldol, altogether that's called a Robinson annulation. Annulation meaning we're making a ring. It's just a micro addition of an enolate followed by an intramolecular aldol. And that pretty much takes us to the end of the material there. Okay? Again, you can look through that mechanism. It's just a micro followed by an aldol. There's some questions you could ask. For example, why not have this attack over here? And if it did, I think the product would be different. I'm not saying that the product I've shown is the only product. I'm just showing you it is a possible product, and that would be an example of a Robinson annulation. Now this here, it can attack something. Well, that's not attacking, that's resonance. If it attacks here, that'd be a 4-member ring. And that's not as likely as the 2 6s that are possible. Okay? All right. Below was my final exam in the second organic chemistry I had in graduate school. It was an open book final exam, starting with commercially available reagents, proposed the synthesis of the following compound known as isoiresin. Synthesis should be stereoselective. These two can react, base catalyst and the Robinson annulation to get this. And from there you can work your way towards isoiresin. If you knew you could do this Robinson annulation, that was a great starting point for this. You can look at that. Now, with such a final exam, you don't know the question before test. You go into and say, oh, you got, I think we had 3 or 4 hours. I can't remember. We are about out of time. Last questions. Last questions. Last questions. Everybody good? Good? No, don't look good. What's wrong?
Sad.
the Michael followed by a aldol. Were you for some reason? We did Michael, we did intramolecular aldol reactions. Okay. Any final question before we dismiss? See some of you this afternoon for lab checkout. Check out the instructions are in the lab manual, yeah? Have a good day, guys.